Hi guys, welcome to my channel Medicine Made Easy. For those of you who don't know me, I am Dr. Shah and I make videos to make complex medical topics simple. Today's video is gonna be all about acid-base disorders. So let's begin. Let's start with acids. A solution with high concentration of hydrogen ions is known as an acid. So what is a base? A base is a solution with high concentration of bicarbonate ions or a lower concentration of hydrogen ions. So what is this pH that everybody is so fond of talking about? pH is the negative logarithm of hydrogen ion concentration. So this solution with high hydrogen ion concentration will have a lower pH, while this solution with a lower hydrogen ion concentration will have a higher pH. So what about us? Our body is a pool of acids and bases, or hydrogen and bicarbonate ions. They are maintained at a fine balance in order to maintain our pH at a range of 7.38 to 7.42. It's important to understand these mechanisms because any disruption of these mechanisms are the basis for the acid-base disorders. So in this video, I'm going to be explaining those mechanisms in a simpler manner. Now the next video will be all about the individual acid-base disorders. Let's start with bicarbonate. Carbon dioxide is formed as a result of cellular metabolism and it gets dissolved in water to form bicarbonate. This bicarbonate reaches the Bowman's capsule of the nephron of our kidney and gets filtered almost entire. After that, it reaches the proximal convoluted tubule. The proximal convoluted tubular cell would look something like this. It has its apical membrane separating it from the tubular lumen and the basolateral membrane separating it from the interstitial fluid or blood. In the basolateral membrane, you have your sodium-potassium ATPase, which transports 3 sodium ions out of the cell in exchange for 2 potassium ions. This process would result in a lower sodium concentration inside the cell, and as a result of that, sodium from the tubular lumen will move back into the proximal tubular cell. This would happen in exchange for hydrogen ions, which would move into the tubular lumen. Now I hope you can remember that the bicarbonate ion filtered at the glomerulus has now arrived at the proximal tubular lumen. This bicarbonate reacts with this hydrogen ion which was secreted to form H2CO3 or carbonic acid. This reaction is catalyzed by carbonic anhydrase. This H2CO3 is unstable, so it breaks down into HCO2 or carbon dioxide and water. This carbon dioxide crosses the apical membrane to travel into the proximal tubular cell, and so does the water. They both react again inside the cell to form H2CO3 catalyzed by carbonic anhydrase. This H2CO3, as I mentioned before, is unstable, so it breaks down to hydrogen and bicarbonate ions. This hydrogen ion is then secreted in exchange for sodium ions, and it will undergo this same mechanism again and gets reabsorbed in the form of water. So I hope it's clear that the hydrogen ion secreted in exchange for sodium ions at this point gets reabsorbed as water at this point. So there's no net loss of hydrogen ions at the proximal tubular cellular level. So what happens to this bicarbonate? It travels through the basolateral membrane and gets absorbed into the blood. In that manner, the bicarbonate concentration in the blood is maintained at a more or less constant manner. So what about the distal convoluted tubule? It has been proposed that a similar mechanism occurs at the distal convoluted tubule as well, but the concentration of carbonic anhydrase at the distal convoluted tubule is low. So we can assume that, or we can come to a conclusion that almost majority of the bicarbonate reabsorption occurs at the proximal convoluted tubule. any mechanism or any process that disrupts these mechanisms would result in an acid-base disorder. Next we have hydrogen ions. Hydrogen ions, once again, when it comes to the nephron, the majority of the hydrogen ion homeostasis mechanisms occurs at the collecting duct. So what about the proximal convoluted tubule? I hope you can remember when I was discussing the bicarbonate ion, I was mentioning that there is no net loss of hydrogen ions at the proximal convoluted tubular level. So let's move on to this distal collecting duct. Let's move on to this collecting duct. You have your alpha intercalated cell at the collecting duct. It has its apical membrane separating it from the tubular lumen and the basolateral membrane separating it from the interstitial fluid or blood. In the apical membrane of the alpha intercalated cell, you have ATPase which secretes hydrogen ions actively into the tubular lumen. And you have ATPase at the apical membrane which transports potassium ions into the alpha intercalated cell as well. So this aldosterone, which is a well-known hormone, influences this ATPase and increases the hydrogen ion secretion at the alpha intercalated cellular level. You can also see this hydrogen ion and potassium ion transport are in the opposite directions. This is to maintain the electrical neutrality of the cell. This hydrogen ion which is inside the cell and which is getting secreted out of the cell is mainly from the water which is inside the cell. We can also see that the carbon dioxide inside the cell will react with water to form H2CO3 or the carbonic acid, which is not a new member to us. We discussed it about in the bicarbonate metabolism as well. And this reaction is catalyzed by the carbonic anhydrase enzyme. This H2O3, as we all know, is unstable, breaks down to H+ and bicarbonate. This bicarbonate is then secreted out of the cells or moves out of the cells via the basolateral membrane into the blood or interstitial fluid, and this is in exchange for an anion or chloride which is reabsorbed into the cell. So I hope it's clear that the mechanisms occurring at the alpha intercalated cells of the collecting tubule is for H+ homeostasis is mainly an active secretion of hydrogen ions out of the cells. We also have another cell in the collecting duct, which is the principal cell. The principal cell has its sodium-potassium ATPase at the basolateral membrane. This is a well-known sodium-potassium ATPase which transports 3 sodium ions out of the cells and 2 potassium into the cells. Why is this important? Because of this transport of sodium ions out of the cells, the intracellular sodium ions in the principal cells is low, and also the intracellular potassium ions will be high. These potassium ions will be transported back into the tubular lumen via the apical membrane. As you can see, this potassium is the one that is being absorbed into the alpha intercalated cells to maintain the electrical neutrality for the secretion of hydrogen ions. Because the sodium concentration is low, the sodium from the tubular lumen will move back into the principal cell. Again, the hormone aldosterone plays a role here as well. It also promotes the action of sodium-potassium ATPase, secreting more sodium out of the cell and taking more potassium into the cells, facilitating this whole process. We have another cell in the collecting duct, that is the beta intercalated cell. Now you can think of this beta intercalated cell as something similar to the alpha intercalated cell, but the transporter located in the opposite membranes. Did you get what I said? I'll explain. here the ATPase is located in the basolateral membrane and it secretes hydrogen ions into the interstitium of the blood, which was not so in the alpha intercalated cell. In the alpha intercalated cell, H plus was secreted into the tubular lumen. Here it's the opposite. And here you have an anion exchanger which transports bicarbonate ions into the tubular lumen in exchange for an anion. And mostly it is thought to be chloride. So it is exactly the opposite of this, where the bicarbonate is secreted into the blood, while here the bicarbonate is secreted into the tubular lumen. So this is the basic mechanism of hydrogen ion homeostasis in the collecting duct. Any mechanism which disrupts this would result in an acid-base disorder. Another quick question. What happens to this hydrogen ion which is secreted by the alpha intercalated cell? Okay, so what happens is it reacts with a buffer. I hope you all know what a buffer is. It neutralizes, in simpler words, it neutralizes these hydrogen ions. So what are the buffers we have? We have two main buffers in the tubular lumen. One is the phosphate buffer, and where the HPO4 2- reacts with hydrogen ions to form H2PO4 or phosphoric acid. And then we have the ammonia which reacts with hydrogen ions to form NH4 plus or ammonium ion. Now out of these two buffers, the phosphate buffer is limited in quantity. You can't increase it more than a constant limit. So when you have a lot of hydrogen ions, if you need more buffer, you can't overcome that demand by increasing the phosphate. But ammonia is not so. You can increase the amount of ammonia buffer in the tubular lumen. I'll explain how in the next slide. So, there is another important thing as well. The nature has devised a nice mechanism where when the pH falls below a constant value, say about 4, this ATPase is inhibited. So when this hydrogen ion excretion or secretion is more than what is said to be normal, the tubule senses it as, oh, something is going haywire. This guy is secreting more hydrogen into the lumen. I should stop this. So this acidic pH here, or the low pH here, inhibits the ATPase. So if there are situations in your body where you need to excrete more and more hydrogen ions out of the kidney, suppose you have a lot of hydrogen ion inside your body, or your body becomes too acidic, so you want to secrete all of these hydrogen ions out of the body. But this guy or this tubular lumen senses it and says, no, I'm too acidic, I want to inhibit this, I can't allow you to secrete more hydrogen. So what now? We want our body to be at the neutral pH. Then your buffer helps. This buffer will quickly come and neutralize these hydrogen ions. So although you have secreted a lot of hydrogen ions, the tubular lumen will not be acidic. So the lumen is misguided that its desired cutoff pH is not reached yet. So this ATPase can secrete more and more hydrogen ions out of the cell. So this buffer system is very important in that manner. We'll be discussing more about this in future presentations as well. So I was talking about these buffers, and I was saying ammonia, the level of ammonia in our body can be increased, and it's the most important buffer that we need. Wanna know why? Let's see. The main site at which the ammonia homeostasis starts is the proximal convoluted tubule. The proximal convoluted tubular cell would look something like this. It has its apical membrane separating it from tubular lumen and the basolateral membrane separating it from interstitial fluid or blood. And inside the proximal convoluted tubule, you have glutamine. Glutamine helps in synthesis of alpha-ketogluteric acid and ammonia. This ammonia is lipid soluble, so it is transported out of the cell into the tubular lumen. In the lumen, it reacts with hydrogen ions to form ammonium ion. Now, this ammonium ion, which is formed in the tubular lumen of the proximal convoluted tubule, travels through the loop of Henle, right down and right up to reach the ascending limb of loop of Henle. At the ascending limb of loop of Henle, you have the same cell, not the same, a similar cell with apical membrane, tubular lumen, basolateral membrane and interstitial fluid. Here what happens is this ammonium ions in the tubular lumen is transported into the interstitial fluid or blood. In that manner, the interstitial fluid ammonium concentration is increased, or there will be a huge load of ammonium ions in the interstitial fluid. How does this help? Well, this ammonium ions is then again dissociated into ammonia plus hydrogen ions. Well, and then this interstitium full of ammonia or ammonium ions they are created by this ascending loop of Henle. Now we come to the collecting duct. In the collecting duct cell, you have the apical membrane and the basolateral membrane. Here, the ammonium or ammonia, which was now there at the interstitial fluid. Remember? Now, our ascending limb of loop of Henle created this huge load of ammonia at the interstitial fluid. That ammonia will be transported back into the collecting duct. This ammonia is then again sent to the tubular lumen. So, now can you remember when we were discussing hydrogen ion homeostasis, I was explaining to you that the H plus ATPase, which was at the collecting duct, secretes the hydrogen ions at the collecting duct, and that hydrogen ion is neutralized by ammonia buffer. So this is that ammonia buffer which helps for us for that neutralization. So here we have that hydrogen ion which was secreted from the collecting duct. They will again form ammonium ion. This is the neutralizing process. So I hope that this process is very clear to you. This ammonia we have a lot of ammonium ions in the tubular lumen of the collecting duct, which has now reacted with which was formed as a result of the ammonia reacting with hydrogen. This is then excreted through the urine as ammonium chloride. That's how the hydrogen ion which was secreted from the collecting duct gets neutralized and excreted out of the body. I hope this is very clear to you all. Today we learned about the basic mechanisms that maintain the acid-base homeostasis. If you like this video, give a thumbs up and share it with your friends and colleagues. Don't forget to click the subscribe button and also to click the bell icon so that you'll receive an update when I upload the next video. If you have any topics for which you need a simplified video, please leave a comment and I'll be making one the next time. So until we meet again, bye bye.